Hello and welcome to this class on thermochemical processing. I am Professor DebRoy from the University Park campus of Penn State, and I am very happy that you are reviewing this very important topic of sustainable steelmaking. Steels are all around us. Transportation, buildings, bridges, roads, agricultural machinery, you name it, we need steel. In simple terms, and we cannot sustain our standard of living without steel. But steel making is also devastatingly polluting. You will see that steel making contributes between 8 and 9% of all the CO2 emissions in the whole world. And so we need to reduce the greenhouse gas emissions from the steel plants. But the question really is, what can we do? How do we reduce the greenhouse gas emission? So in this class, we are going to be reviewing the challenges that we face in reducing the CO2 emissions. We will review two specific, very promising technologies that we are now exploring, and also we will see that technology alone will not reduce the carbon dioxide emissions in the environment from steel plants. We need to do a lot more. We need to change our policies, and we need to have a national will about doing it. What is the current status? So what is the source of the carbon dioxide? What technologies do exist today? What is the status report? And what policies do we need in order to achieve our goal of reducing the greenhouse gas emissions in steel industry? The reading materials are available in part 3 of thermochemical processing notes that you have, and also an article and also you may review an article from my book on innovations in everyday engineering materials that has a chapter on transition to sustainable steelmaking that is also copied for you in the thermochemical processing part 3 class notes. So buildings, bridges, transportation, power generation, agricultural machinery, distribution of clean water, anything that is important needs steel. And we need about 1.7 billion tons of steel per year globally to sustain our standard of living. So we cannot do without steel. But you heard that it is very polluting. It discharges, steel making discharges about 1.8 tons of carbon dioxide per ton of steel produced. And in 2018, for which we have data, steel making contributed to 8.4% of all greenhouse gas emissions in the whole world. So CO2 emissions contribute to global warming and greenhouse gas effect. So we are contributing in a major way climate change and the rise of the sea levels. We just have a few years to significantly reduce greenhouse gas emission or face the 2-degree rise in temperature from the start of industrialization, which we have been told by scientists that if we allow the temperature to rise 2 degrees above the temperature at the time of the start of industrialization, there will be catastrophic problems. So the failure here is not an option. We need to control the CO2 emissions. Otherwise, the consequences are really, really bad. So what are the challenges? Why can't we do it very soon? Well, steelmaking technology, remember, has been perfected over a long time, over centuries. And the steel is a very inexpensive but a necessary commodity for sustaining our standard of living. And how inexpensive? It's comparable to the cost of bottled water or soda or coffee on a weight basis. So replacement of the current technology is difficult because the greener technology will have to manufacture the same amount of steel that we now make in a devastatingly polluting technology. And for that, we need a very large investment, capital investment, to test, deploy the greener technology. And steelmaking, of course, is a complex multi-unit operation, as you have seen, and they all contribute in some ways to the greenhouse gas emission. Also, the low profit margin of the industry means that they do not have the capital to develop, test, and deploy any new technology. And the new green technology must be implemented throughout the world. Otherwise, when we discharge the CO2 in the environment, the whole world loses. So in this discussion today, we will review the source of the CO2 emission, why steelmaking has such a huge footprint, and the current status of greener technologies, and what policy changes we need in order for the future to be better. Sources of CO2 emission. There are many. Multiple routes of steelmaking, such as basic oxygen furnace, electric arc furnace, ladle furnaces, the manufacture of pig iron in the blast furnace. Each blast furnace, the bigger ones at least, are making 10,000 tons of hot metal, not in a year, in a day. It is that productive. And then there are many supporting units, many auxiliary units in steel plants, all contribute to the emission of CO2 directly and indirectly. So what are the steelmaking routes? Let's review. Oxygen steelmaking, right? Where we take an oxygen lens and we supply oxygen in a basic oxygen furnace at a rate of about 18,000 standard cubic feet every minute in the form of a supersonic jet of commercially pure oxygen, and impinge that on hot metal obtained from the blast furnace to oxidize the carbon, right? And other alloying elements such as silicon and manganese. The carbon dioxide that we produce by oxidation of carbon burns at the top of the furnace and produce carbon dioxide in the furnace exhaust. Then we have the electric arc furnace steelmaking. So heating and melting of the recycled scrap can be done, and it consumes a large amount of electric current. Oxygen lancing is provided for oxidation of carbon and other alloying elements. Heating and melting of the recycled scrap consumes a very large amount of electric current, and oxygen lancing is necessary for the oxidation of carbon and other alloying elements. They also contribute to the CO2 that is discharged in the environment. And remember, anytime we use a large amount of electricity, we need to look at the source of that electricity. If the source is fossil fuel, that is also indirectly contributing to the greenhouse gas effect. So there are two sources of greenhouse gas emission that originates from the electric arc furnace. The first one is the oxidation of carbon that produces carbon monoxide, which then burns and produces CO2. And second, the huge amount of electricity that is consumed in the electric arc furnace. The origin of that electricity is very often burning of the fossil fuel that indirectly contributes to the greenhouse gas emission. And heat is also generated by supplementary gas burners that produce carbon dioxide. So that's another source of carbon dioxide. And of course, the steel making itself, that means steel making involves reduction of the carbon content of the melt. And what happens to the carbon? Well, we oxidize it by supplying oxygen through the oxygen lands. So electric arc furnaces do contribute a huge amount of carbon dioxide to the environment. Similarly, there are other smaller quantities of steel that are made in ladle furnaces. We call them secondary steel making, and those are mostly refining furnaces. We can adjust composition, and we also oxidize alloying elements and carbon. So they also consume energy and refine the steel and produce greenhouse gases because these are so energy intensive. And we shouldn't forget the contribution of the blast furnace iron making. So we charge iron ore, mostly hematite or magnetite, coke, which is primarily carbon without the volatile matter, a flux such as calcite or dolomite, which are carbonates, calcium carbonate or calcium magnesium carbonate. We supply air, and oxygen in air reacts with carbon in the coke to produce heat. And also it produces carbon monoxide, which travels upwards, reduces the iron oxide, and produces carbon dioxide. So that is another source of greenhouse gas. And carbon dioxide is also generated by other reactions like decomposition of limestone. Limestone is calcium carbonate that upon heating produces calcium oxide that forms the slag and carbon dioxide. And there are many units that support the blast furnaces that also contribute to the carbon dioxide discharge. Sintering units, for example, they require combustion of fuels and recycled gases and produce CO2. Coke ovens, of course, they burn some amount of coke and discharge CO2. Then remember, the blast that is fed to the blast furnace has to be heated, and they are heated in what we call hot blast stoves. And because we need to heat them using gaseous fuel, they also contribute to the CO2 discharge from steel plants. And then there are many auxiliary units, just far too many to all include in this lecture. But take, for example, the steel that is produced in the basic oxygen furnace or the electric arc furnace. In most cases, to produce continuously cast slabs, then they are rolled and forged into finished products, but the continuously cast products may be stockpiled in some cases, and later they have to be reheated for further processing like rolling, forging, and those reheating also produces carbon dioxide because we are burning fuel. Rolling mills consume electricity, and most of the electricity is produced by burning fossil fuels. So ultimately, they contribute to carbon emission in the environment. The steel industry has to be credited with reducing the amount of energy they spend per ton of hot metal. If we take 1960 as the standard, and that means in the year 1960, the energy consumption per ton of steel, if we allocate a number 100 for that year, in 2017, we consumed only half of the energy to produce the same amount of steel. So the steel industry has made significant progress in using of energy in the steel production. But that is not enough. We need to reduce it. So one possibility is that we use hydrogen instead of carbonaceous fuels like coke. But the problem is, if we use electricity to generate the hydrogen, which then we use in the steel plant, we are still using the electricity, and we have to stop and worry about where the electricity is coming from. If the electricity is coming from the burning of fossil fuel, that again is discharging greenhouse gas into the environment. So that is not a long-term solution. And so we need to look at other technologies for the production of iron and steel. And that is one of the things we should focus on. And two of them we are going to be reviewing today is called top gas blast furnace recycling and Hisarna iron making technology. So both the top gas recycling and Hisarna iron making technologies are two of the processes we review next. So currently, blast furnace uses carbon for both heating of all the charges, and also for the reduction of iron oxide to iron, because the iron ore is oxide ore. Whether it is hematite or magnetite, we need to take out the oxygen from iron and to produce iron metal. So the reaction of oxygen from air with coke produces the heat as well as the reductant CO. And reduction of iron ore and decomposition of the carbonate flux, calcium carbonate or calcite, and magnesium carbonate, calcium carbonate mixture that we call dolomite. But their decomposition produces CO2, which together with the unreacted CO and nitrogen leaves the blast furnace exhaust gas. So the improvements that we are thinking about in the top gas recycling blast furnace replace the air with commercially pure oxygen to avoid heating large amounts of nitrogen. That will certainly reduce the energy requirements. And then the exhaust gas now, when we don't have any nitrogen, will contain CO and CO2. And CO2 will be separated from the exhaust gas and stored for other usage. So we have a plan not to discharge the CO2 into the environment, but instead we separate the CO2 from the blast furnace exhaust gas, and the remaining carbon monoxide we can recycle into the blast furnace to reduce the coke rate. That will also be very helpful. So here is a schematic diagram. We are charging the ore, the coke, the sintered ore, as well as the pelletized ores. So basically ore and coke and flux we are charging from the top, and the oxygen is introduced from the tuyeres, and we can take out the hot metal and the slag from the hearth of this furnace. And the exhaust gas we need to focus on. We separate the exhaust gas from the dust, and then we absorb a portion of the exhaust gas in a suitable absorber like zeolite that can absorb carbon dioxide. And after we separate the carbon dioxide from the carbon monoxide, we take part of this gas, feed it near the middle of the stack, and the other part we supply down below just above the tuyeres. So carbon monoxide is recycled and carbon dioxide is separated. So we are not discharging the carbon dioxide in air. And second thing we are doing is that we are reducing the energy needed for the production of iron by taking out the nitrogen. Nitrogen does not have to be heated because we are not supplying any nitrogen in this process. And the carbon consumption will be reduced from 470 to 350 kg per ton of hot metal due to recycling, because we are recycling carbon monoxide. Hisarna process is a process for manufacturing iron. Instead of using the blast furnace process that pollutes in a very big way right now, this process seeks to replace the blast furnace process. It produces liquid hot metal and does not require any coke, separates the CO2 from the exhaust gas, and another advantage is that we can use very fine ores. So we don't need any pelletizing or sintering units as we need to operate a blast furnace. So there is no need to use the pelletizing and sintering units. We also don't need any coke ovens because we are not using coke. So all these three plants are not needed, so they do not consume energy and they do not discharge any CO2 directly or indirectly into the environment. 20% reduction of energy usage, 20% lower CO2 discharge, and saving of manufacturing cost of liquid iron are attainable compared to the blast furnace process. So this is a big improvement if they can be deployed. This was demonstrated in a pilot plant and sustained for 6 months of trial in 2017 in the Netherlands, in Tata Steel's plant. The challenge here is much lower productivity than the current blast furnace technology and the need to establish its cost competitiveness. The secret is that clean steel is going to cost a little more, and we need to pay for cleaning of the steel. Here is a schematic diagram of the Hisarna process. So what we are doing is that we are supplying the ore. This time it is not pelletized or sintered, it's just plain fine ore. And we are also supplying some oxygen in a cyclone. And iron ore fines and oxygen is introduced near the top of the furnace. So right here, and a cyclone facilitates rapid heating and melting of the ore. And coal and oxygen are introduced in the lower part. Here is coal and oxygen introduced here. And oxygen reacts with carbon monoxide to generate heat and produce carbon dioxide, which is withdrawn from the top of the furnace. And high concentration of CO2 in the exhaust gas means we can easily separate the CO2 and store it for further use. Powdered coal is introduced in the lower portion of the furnace, and it reduces iron oxide to liquid iron, which settles at the bottom of the reactor and can be withdrawn from there. And slag is separated from the hot metal by taking advantage of their difference in the density. So slag floats on liquid metal and can be very easily separated by taking advantage of their density difference. Hisarna process has been tried in smaller pilot plants. About 60,000 tons of iron per year is its productivity of the pilot plant, which means it needs to be scaled up to match the production of modern blast furnace, which is a very tall order if you think of it, because the blast furnace one furnace produces 10,000 tons of hot metal per day, not per year. So we will need many plants of Hisarna to match the blast furnace productivity. But the advantage is that we can avoid the coke ovens, sintering, and pelletizing plants. It has less stringent requirement for the quality of the ore and coal, so it would need less energy. It would generate CO2 at high concentrations that can facilitate its capture and then further reuse. And these attributes have been already demonstrated in a pilot plant scale. The disadvantage is that the scale up and cost competitiveness of the iron produced in this plant will have to be demonstrated to make a business case for the use of this process. So why then do we need policy change in the governmental level for greener steelmaking? Today, there is no well-tested technology that can match the productivity of the current steelmaking. And don't forget, we need the steel. We consume a very large amount of steel in every venture that we think of, starting from agricultural machinery to distribution of clean water, to generation of electricity, to transportation, buildings, bridges, you name it, we need steel. And how are we going to make steel in that scale is an important question. Can we make it at a cost? Can we make greener steel at a cost that compares with the cost of bottled water or coffee or soda? That is another important question. Are we prepared to pay more for cleaner steel? Modernization of technology and reduction of CO2 discharge will make steel more expensive. There is no two ways about it. And we need policies to support the use of high-cost green steel. And we also must comply with the Paris Climate Agreement. That's just a good beginning. So there needs to be some amount of penalty or tariff for trading steels that have been produced across the international borders so that people who are producing pay for the improvement of the steelmaking technology and for their deployment. And governments can also mandate using less polluting steels in public work programs that the government is paying for. And we should be ready to spend a little more money to be able to do that. There are some isolated incidences of good news coming from the steel sector. Like Sweden, there is a program called H2 Green Steel that has a budget of $3 billion to produce green steel beginning in 2024 using hydrogen produced with renewable sources of energy. So by 2030, it expects to produce 5 million tons of zero emission steel. This is too little, but at least this is a good beginning. In Germany, they are building plants by 2025 to produce carbon neutral steel using hydrogen from renewable sources. So they don't contribute, this energy does not contribute to greenhouse gas emission. Their goal is to produce about 400,000 tons of green steel per year by 2025 and increase that to about 3 million tons by 2023. It now produces only 13 million tons of steel per year. Nippon Steel signed a memorandum with Rio Tinto of Australia. Rio Tinto is a major metal producer and iron ore company, and together they will develop low-emission steelmaking technology. They seek to integrate Rio Tinto's considerable experience in iron ore processing and Nippon Steel's leadership in steelmaking technology to establish a new manufacturing process with low carbon emissions. So these are all good news, although they do not go far enough to satisfy what we really need. So if we pause and review the current status and the outlook of the sustainable or greener technologies, 1/3 of the steel that we consume today comes from recycled steel. And that is a very good news because the recycled steel uses just 1/4 of the energy that is necessary to produce steel from iron ore. And so we have made significant progress. And progress has also been made in reducing energy consumption throughout the steel plant. And we have reviewed several greener technologies in the laboratory and plant scales, and there are several promising ones, but none that can match the productivity of the current technology, and that is one of the focus areas now. Also, modernization of the technology in reducing the CO2 discharge will make steel more expensive. Okay, so we need policies to support the higher cost green steel, and groundbreaking innovative technologies can potentially revitalize the steelmaking technology, and that is something that will help everyone in the world. So today we reviewed the challenges and the sources of CO2 emission in steelmaking. And we reviewed the current status of greener technologies and top gas recycling blast furnace and Hisarna process seem to be promising technologies, although their productivity cannot match the current productivity of blast furnace iron making and basic oxygen and electric furnace steel making policies. So we need policies to implement the greener technologies, and all of these materials are available in the uh, PDFs of the PowerPoint slides and in my class notes on thermochemical processing part 3, which is available on Canvas. So that is all for today. Thank you and see you soon.